let us switch to this. Alright. Okay. Alright. So for the first, we're gonna do question 1 of chapter 4 homework number 4. For this, we are using the node voltage method. Let me draw the circuit. Something like this. What does that say? V sub S. V sub S, not V sub X. And with current going this way. Alright. Alright. So we have our circuit here. So the first step we can take is for the node voltage method, our goal is to find essential nodes. And essential nodes are nodes with 3 or more elements. For example, here is an essential node. Here, and here. This would not be one because it's only 2. Not essential. And now we need to ground one of these nodes. Which one do you think? Typically you ground the one on the bottom. It doesn't matter which one you ground. And a good note to have is the one that you ground should have the most elements connected to it. It makes it easier. Um, but for this one, they all have the same number of elements, so we're just gonna ground this bottom one here. Connected to ground. Right. And what this node is here, you'll see what it ends up doing shortly. Right. So that's the first part of this homework, is figure out how many essential nodes there are. Well, there's 1, 2, 3, 4, obviously, that I have circled. That's the number of essential nodes. Now the next part it's asking is, it wants you to ask, um, write a KCL at one of the nodes, right? The node way. Um, we'll label them, it has it labeled, we'll label this one V1, V2, V3. And that's what each of these nodes will be, right? So KCL, we have to do the currents going into the node. So we have, obviously, I have S. We'll do, first, let's focus on V1. V1 only. So V1, KCL. We have IS here going into it, so negative IS. Note, voltage is equal to R times I. We can rearrange this as V over R is equal to I, right? For example, we'll make for an example, to do a KCL here, we don't have a current at this point, but we have the resistance and we have two voltages from V1 minus V2 divided by 1000, which is the resistance, right? V divided by R. Now this may be looking a little confusing, V1 minus V2. Well, you're saying the current from V1 to V2, that's how you get V1 minus V2 is you're going from there to there. That'll point the current this way, right? And that's the voltage drop over that point, because the voltage drop, which is the voltage divided by the R, will give you that current, right? And the voltage drop is V1 minus V2. And now we'll do the same thing for the one up here. We're gonna do, let me skip this real quick. We're gonna do the next one. Plus V1 minus what? Well, we're going from V1 to the 5K resistor up here. And then we're going to V3. So the path is V1 minus V3 divided by 5,000. And what does this KCL have to equal? 0. Okay. Now that is the other part for this extra credit. That is part B. Now we're going to do part C. Let's do a KCL at the node labeled V2. This is also noted. This current I sub S, that value is given to you as whatever it may be, but this is just the algebraic expression. This is for V1. Right. This is for V1. I'm gonna erase this, or I can just do this. Hold on. Make my work look nicer. Copy. Alright, move that drawing down here. Let's do one at V2. Alright, let's do node V2 KCL. Using the nodes stuff. Alright, so we have 3 resistors. Alright, let's do these two right here. So from V2.
Okay, we're back. Actually went ahead. I do this one over again. We're doing the node at V2 now. Recording stopped for some reason, which is weird. Alright, we're going to do the node at V2. From V2 minus V1 divided by 1000. Right, we're going from this node here to this node. And that current will be directed this way. It's just the perspective of the node kind of thing. But that's the voltage drop. That indicates the direction. If you're going from V2 minus V1, when you solve it, that current will be pointing this way. Plus V2 minus V3 divided by 8,000. Now here's the trickier part. V2, but it's going to this grounded one here that we made at the beginning. So it's going to be V2 minus 0 divided by 3,000. And this is all with the principle of this formula here, which originally is V voltage is equal to resistance times I. It's just rearranged. These are each voltage drops over the resistor. This is equal to 0. That's the KCL for the node method, or whatever, node voltage method at V2. I haven't answered this on my extra credit. Let's see if this is right. Fraction plus fraction plus another fraction. Oh, positive. Alright, I'm back, and that was right. That is the correct KCL there. Looking good. Okay, for the next one. Alright. Let's see, where's my pencil? There it is. Let's do V3. Stupid ad. Okay. Alright, for this next one, we're going to do a node at V3. Right, this one here. I think, right? It wants V3, right? Yeah, so we're doing V3. Okay. So V3, node V3. Alright, so we're going to do, we'll start at the top resistor. We're doing V3 minus V1 divided by 5,000 plus V3 minus V2 divided by 8,000 plus V3 minus, right, like the other voltage sources at the nodes, minus Vs. That's tricky. We're given the current, and by default, we can just instead do the minus I sub 0 current. Which is that given to us? It is not. There's no actual resistor in between those two nodes, the V3 and V sub S. It's a little tricky. Maybe you would express it as V sub 3 minus Vs. We're assuming that the voltage Vs that this current is entering, because the current is entering I sub 0, it is entering. Let's see. Let me see. Let me figure this out. All right, I'm back. So, wasn't much to it. In theory, we have this current here, I sub O here. What you do is take this current that's flowing through this 2K resistor and this voltage source. They're the same, right? And they're in series. So we take V sub S divided by 2000. That'll give us I sub O. That's simple. Which 0.06 is what it is. Let me change the song real quick. What should we play? I'll go for Coldplay. Alright. So this equal to 0? So yeah, that'll give us, V3. Just add plus the... Yeah. Let's plug that in real quick. Let's check to see if this is right. Alright. Must note. This is not correct. I found that it was V3 minus Vs, which is that source, divided by 2000, equal to 0. Since these are in series, to make this seem more sense, you can swap these locations so that the resistor is in between the two voltage sources, which will allow you to do your node analysis entirely. V3 minus Vs. Since they're in series, you can't swap their locations. According to this. It's kind of goofy. Alright, next part. Now we need to solve for the actual voltages. What are the voltages at V1, V2, and V3? Well, this is the hard part. And it's the most pain in the ass part, if you don't have a fucking graphic calculator. Now that we have all these, right, we must isolate the constants on the right side where the zero's at, and we must isolate all the variables to what they correspond with, right? we must create a matrix. Alright, so in order to do that, we're going to do that on a whole different page. This is a major pain in the ass. I hope he does not make students on a test, or else I'm going to have to buy a whole damn calculator. Alright, so we're going to write all the equations that we have required. I'm just going to write down the one the second one, because I have the others on my iPad. Okay. 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 This is for, this is the second node, right? I'm gonna copy and paste the other nodes down real quick. Copy, paste, copy, paste. Try to organize these by their node number. Okay. Alright. So what do we do now, right? How do we find these voltage sources? Well, we gotta do a little matrix. Matrix. So we know I sub s in the first one is given to us, and we can add that over to the other side and make it a constant on the other side, which is going to be 0.01. Oh my bad. Alright, so for the first one, we're going to have equals 0.01, right? We're going to separate all the variables, like to v1, like a linear equation type of deal. 1 over 1,000. That's one of the v1s, and 1 plus 1 over 5,000. Plus v2. 1 over 1,000. This number is negative, though. Let me move this over. We have v3 also. Negative 1 over 5,000. So we have 1, 2, 3, 4. 1, 2, 3, 4. Okay, we're good. Alright, that's the first one. Do our matrix. Now let's do the next. Node 2 matrix. We'll isolate v1. So we have v1 here also. I'm going to keep them in order. Negative 1 over 1,000. And that's it for that one. 1 over 8,000. 1 over 3,000 plus v3. We have no constants in this one, so we won't be, we'll just have it equal to 0. And there's only 1 for v3, and that's negative 1 over 8,000. Next one is, V3. Okay. Do we have any V1s? We do. Negative 1 over 5,000. That's it. Plus V2, there's one V2. Negative 1 over 8,000. One more, we have some V3, so 1 over 5,000. And we're going to have plus a negative 1 over 2,000. And we're going to have that equal to 0.06. This constant here. V of S will be 120 divided by 2,000. What we had originally that first time. But we didn't think about the node entirely, so. Anyways. That should be it. Let me make sure. I think they give us it to us. Okay. Now let's put it into my matrix calculator. See what we get. So if you were to do a matrix, right? If you were to do it realistically, you would have to, sum up the V1s, the V2s, and the V3s, like for each one, so you have one number for each of those to plug in, right? And you'll have like a 3 by 3 matrix here. And that'll be equal to like 0.01, 0, and then 0.06. This side of the matrix. And then you'll have your variables here. V3. Right? And you have all these numbers in this little matrix here, which will be these ones up here. It'll be 3 by 3. Well, we have to divide this matrix over, so it'll be raised to the negative 1. So you'll have this matrix, whatever it is that you fill it in, to the negative 1 times our constants. And that'll give us V1, V2, and V3, top to bottom. Right? So let me actually do that. So for the first one, we'll have 1 divided by 1,000 plus 1 divided by 5,000. Second one, negative 1 divided by 1,000. Third one, negative 1 divided by 5,000. Next one, negative 1 divided by 1,000. Next one is going to be 1 divided by 1,000 plus 1 divided by 8,000 plus 1 divided by 3,000. Negative 1 divided by 8,000. Negative 1 divided by 5,000. And then negative 1 divided by 8,000. Then we'll have 1 divided by 5,000 plus negative 1 divided by 2,000. Alright, that's going to be our first matrix that I'm storing in a variable called A. And we're going to go to the B matrix, which will be our constants. Top will have 0.01. The middle one will have 0. Item stored. 0.01. 0. 0.06. And this constant matrix B is going to be 3 rows, 1 single column, nothing too crazy. So we'll have B and A. This will be raised to the negative 1 times B okay. B1 is equal to so I got negative 58.13, and then I got negative 51.83, and then I got negative 139.64. Even the question refers that you get the, Alright, so you definitely need a calculator for this problem. Like, there's no way you're doing it without it. I don't think these are right. I don't believe these numbers should be negative. Let me see. No. I did something wrong. Let me see if my arrangement's correct. Alright. Let me check. So, according to this, I set it up correctly. Let me make sure my numbers are right again. Plugging in negative 1 divided by 5,000. Negative 1 divided by 1,000. Then we have 8,000 plus 1 divided by 3,000. Same number. Same number. Same number. Same number. Same numbers. Okay, where did I mess up then? Let me go to my B. 0.06. All my numbers are right. Make sure my process is correct. Yeah. No, yeah, these numbers are right. I think I just need to make them positive. Um, okay. I think it is. I got 58, 51, and 139 point whatever. It's wrong. It's wrong. That's inferiority. The hell? My numbers are plugged in right. Hmm. Hmm. What the hell? Hold on. Alright, I tried another calculator and it was still right. So. Hmm. I mean. Hmm. I don't see how this is not the right answer. It is what I got from the matrix. Hmm. 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 We're in volts. So. I mean. I mean. Not adding up. Hmm. Alright, I figured out where I went wrong. Holy shit, it took me like forever. This is wrong. Plus 1 over 8,000 plus 1 over 2,000. That gives us the right matrix. Because if we look at V3 here, 1 over 5,000, 1 over 8,000, there should be a plus. That should have been a plus, my bad. Plus 1 over 2,000. Right. That's my mistake. And now with that, we can find a lot of things. Voltage. 75. V1 should be 75, V2 60, V3 is 100. So power. Okay. Power is equal to voltage times the current, or power can be equal to what? Lord have mercy. Oh my goodness. Power, voltage squared divided by resistance. Okay. Alright, we're gonna attend to this one now. Enough drawing. We're gonna switch to this. Alright. Oh, you silly duck. Voltage squared divided by resistance. V1, which is 75, I believe, squared, divided by 1,000. It's in milliwatts, by the way. So I got 5.625, but it's gonna be 5,625 whole. Oh, wrong number. 5,625. This is already 10 milliwatts, I'm pretty sure. 260. Actually, how do you calculate the power? How would you do that? How do you calculate the power? I actually don't know. And the power for the source, current source. Power is equal to voltage times I. Maybe, oh yeah, we'll do the voltage drop, not the actual. So we'll do V1 minus V2. V1 minus V2 is 15 squared divided by 1,000, which is 225. We'll do the voltage drop because you know this stuff. This one's already 10. V2 is just V2 minus 0, so it's just going to be V2, which is 60 squared divided by 3,000. 1.2, 1200. We'll do the voltage drop. We'll do V3 minus V2, since V3 is 900 minus 60 squared divided by 8,000. Depends on which way you go. V1 minus V3. Yeah, we'll do the sign convention for this one. 60. No, 75 minus, it's negative 25. But negative 25 squared is positive. Oh, so when you're squaring it, no matter what, it's positive. Okay, that's cool. Doesn't matter. I forget that we're squaring it. It'll be 125. here. P voltage source in millivolts. We already knew that. The voltage source is 120. So, and the volt. Oh, we know the current though, right? Yeah, we do know the current. The current is equal to 0.06. 0.06 times the voltage source. 7200. And E300 minus 120. 20 squared divided by 2000. It's going to be 200. There you just do 0.06 squared times 2000. Doesn't give us the same thing. Or is it 2000 squared? No. Power is equal to voltage times current. Power is equal to resistance squared. And I don't even know. Let me look at the chart. Power. Oh, it's current squared, yeah. What's the current? We said it was 0.06. That's what we said. Squared times. Money squared. Now it says 7200 for some reason. And for the voltage here, we have voltage and current, so we'll just do 120 times 0.06. We're getting the same numbers. Interesting. That isn't wrong. Yep. Doesn't even feel right. Why do they fuck up again? Alright. We're back. This one's wrong here. And that's because we're looking at power. I'm stupid. This is a 10 milliamps, right? Which is equal to 0.01 times 75, right? The power, V1, is going down into ground, so the power throughout here is 75. So 75 times 0.01 gives us 7500 milliwatts, which is 0.75 watts. That's that number. Power at the voltage source, P2. Let me think. To be honest, I don't think we ever knew I sub 0, actually. The current, technically, by default, should be... 120 minus 100 divided by 2000. 0.01. This actual voltage source this whole time was 0.01, which is equal to IS this whole time. So 0.01 times 2,000, no, 0.01 squared times 2,000 is 0.2. So this ends up being 200 and 120 times 0.01 is 1.2 watts, which is 1,200 milliwatts. Alright, the rest are right. You son of a gun. Passive sign convention, so some of these are negative. Oh, this is delivered. The current's going against, so it makes it negative, from negative to positive. This is also negative, because this power is going down. This is also entering the node, this current here. And that should be that. I'm going to what? I think my zeros are wrong. 1, 2, 3. Oh my god, they are. This is negative. This is negative. And this is negative. Oh, my carryovers are wrong. Oh, 1.2. Alright, this 1, 2, 3. Okay, that's right. 0.225. Somebody text me. Point 2. Okay, I think this is right now. Thank you. Lord have mercy. Find these. The voltage. It's just the voltage drop. Positive and negative. No. 10. And here we have voltage drop 75 to 100. I say it's negative 25. If we're going this way. Yep. Mesh current method? Yeah, we're not going that crazy. Alright, here's the next one. Holy smokes. Oh, I don't know if I want to do this again. It's just painful. Okay, let me draw this circuit. Alrighty, let's switch the screen. Alright. We're not linked. Let's link up. Hold on. 1 second. Let's get this airplay going. Alrighty, right. Let's find those essential nodes. Okay, so we have one here, another here. I'll make it a little bit bigger. We have another one here. And we have one down here. I'll make this ground. Okay. So, I'm gonna do this. Let's make this one be 1. Actually, let me Let me move this over to my other screen. There we go. Whoa. There's 1, 2, 3, 4. 4 essential nodes. So let's put that in the answer real quick. I want to see where it labels our voltage points real quick. Alright. VA, VB, VC. Alright. We're using the alphabet. This is more common usually. Actually, no, I feel like the numbers are VC. So, now it's going to ask us. Once you have identified the essential nodes, you must choose one of the essential nodes as a reference point. It's gonna tell us first to pick our Now, the first question is asking, or the part B is asking, when a branch of a circuit that connects two essential nodes contains only a voltage source, a special case exists. As you will see in part C, how many branches in this circuit contain two essential nodes and contain only a voltage source? Well, from VA to V1, right, these two here, we have this case and this case here. So there's a total of 2. So part C, label the essential node voltages. So when a voltage source is the only component in a branch that connects the reference node to another essential node, the voltage of that essential node is known. For example, the 8-volt source in the circuit here is the only component in the branch that connects the node labeled VA to the reference node. So VA is equal to 8 volts. This is a special case. There is no need to write a KCL equation at VA because the voltage is known. This special case also exists for the branch that connects the nodes VC. And I agree with that, because there's nothing in between these two nodes here and here. There's only a given voltage source. And the voltage source in a circuit, without any resistors meddling in the way, is equal. Right? There's nothing absorbing the power or voltage in between. So we know V1 and V2 already. So VC is 17 volts. We already figured that out. VC, this is 17 volts. And V8 this is 8 volts. Right? Because this is 8, this is 17. So this is 17. Okay. Alright. So now, replace these symbolic labels with their voltage values as shown in this. Now, we can find VB. We can write a node at VB, right? We can do a KCL at VB now, since we know all the voltage sources coming into there. So for VB, we're going to do VB. And we're going to do VB minus 8, which is VA, divided by 25 plus VB minus 17 divided by 140. Right? Yeah. Plus VB going to ground minus 0. Alright, we're going to ground. This ground here. Let me click here. Get rid of that extra stuff. VB divided by 10. Right. We're going straight to ground, so we just have that as that. Alright, so we have this. We have this equation for VB. Now we're gonna do the next. Holy shit, there's 3, 6, 7 more parts. Oh my god. How is there that many? Alright. V, is there another figure? I hope not. Fraction. Let me put in this real quick. So B minus 8 divided by 25 plus the fraction V sub B minus 17 divided by 140 plus the fraction and divided by 10, what we have already written up here. And that'll give us a correct. Nice, nice. Alright, what is the voltage at BVB? Right. We should be able to find this out. We should be able to find this out because we know all these we know the one variable that we have in this equation, which is VB. So let's pull some things out. VB is equal to 1 over 25 plus 1 over 40 plus 110. Now we have two constants. They're both negative, so we can add them over to the other side. Let's let them equal. Alright, so we have 8 over 25 and 17 over 140. We'll add those together in my calculator. 8 divided by 25 plus 17 divided by 140. 0.441. 0.441. I think that's enough to get the right answer. And then we can add these fractions that are connected to VB and then divide them over. 1 divided by 25 plus 1 divided by 140 plus 1 divided by 10. 0.441 divided by 0.147, which I got. And we get a beautiful number. Oh, where am I? We get a beautiful number, right? We got VB equal to 3 volts. Beautiful. Beautiful number. Nice. Nice. All right. Okay. So the next question is asking. All right. Next question is asking. Let's go back to our picture. What is the current here? What is this current? Well, if we use the node in that direction, it's from this node over to this node. So we're going to do 17 minus 3 is the voltage drop divided by 140. And that should give us the current I that we're looking for. Let's see if that's right. 17 minus 3 is 14 divided by 140. We get a nice number like 0.1. It wants it in milliamps, so we're going 1 to 100 milliamps. Right? Yes. Correct. Okay. Oh, shit. We got a new circuit now. We got a bunch of new circuits. There's 2 new circuits now. Oh, it's just 1 new circuit. Okay. Now we got a new circuit. Just forget the circuit we're doing now. We have a new problem. Part G. Okay. Part G. We have a node here. we have a current, what is that? A current controlled voltage source right here. Surprised we didn't have that on the test. 9.
Step outside, I need my peace. Take one down, I need my peace.
Oh shit, I forgot I'm still recording. Alright, we're back. I'll have to edit that out. For the most part. Alright, let me see what I got going on here. Okay, let me finish all these. We got board, kilo ohms here. 2 kilo ohms here. 8 kilo ohms. 5 kilo ohms. Alright. So the current, we're given a current controlled blah 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 blah. I sub A is the current up here. Let's do the essential node stuff. Here's one. Similar to the others, to be honest. We got one down here. We'll ground the bottom one again. And for reference, it actually doesn't matter which one you ground. But in most cases, the bottom is the best. because it's easier. We're given V sub S, right? This thing up here. It's 200 volts. What else are we getting? That's pretty much it. Okay. What's the question I want to ask? Oh, that's not I sub A. That's a Greek letter, but we're going to keep it as I sub A. V X Y X. All right. So, before we go any further, we're going to label these points VX, and I'll tell you why I labeled this one a certain way in a little bit, and VA and VX. Now, I labeled these the same, right, because of this voltage source up top, VS. And it is going directly to that node there for the power being supplied to the circuit. And there's nothing in between the nodes, no resistors, no nothing. There is a current, but that doesn't have anything to do with that. There's nothing in the way, right? So, 200 volts is equal to V sub X. Right? And now, it wants us to do, let's read the question. Consider the circuit shown here, which has a voltage source blank connecting to essential nodes, and you use the node voltage method to find the power dissipated by the 8 kilo ohm resistor. By now you should be able to recognize that the circuit has 4 central nodes. Yep, they usually do. Every single question has that. Identified in this circuit diagram by the solid circles, we will choose the bottom node as the reference node, like I did, and remaining essential nodes with symbolic voltages. Once we solve the circuit, we can use the value of F sub Y to calculate the 8 kilo ohm resistor. The circuit is redrawn here. Recall that V sub S is equal to 200 volts. Note that this circuit has a branch that connects 2 essential nodes and contains only a voltage source. The branch, blah, blah, blah. Special case for the nodes voltage method. Yes, the special case is the V sub S and these 2 VXs here. What is known is the difference between those 2 node voltages. What is known as the difference between those 2 node voltages, which can be written as a constraint equation. Enter the constraint equation that defines the relationship between Vx and V. Alright. So we're going to do a KCL. So V sub Z. Alright, so this question wants to know, what is V sub Z minus V sub X? What is V sub Z? What is that? Oh. This is V sub Z. Alright. 0. Hold on. Okay. So, like I said, um, I mean, I wasn't entirely wrong, but for this case, v sub z, right? V sub z minus v sub x. It isn't entirely equal to. I mean, they are, but at the same time, they're kind of not. The power of 200 volts is distributed to V sub z, which the polarity of the battery gives it its sign, plus to the V sub z, which is on the right, and V sub x on the left being negative. So V sub z minus V sub x is 200 volts. Right? Because the negative minus the negative makes it positive, so they add together. Now, in this case, you can create a supernode, which basically, since from positive to negative, this whole thing is basically a 200 volt power source. And that makes it a supernode. And you can still do KCL with a supernode and everything. But that is what it is. When you have two essential nodes, right, here, and V sub x and V sub z, and between it there's a battery, right, you can do a supernode. Now, in the case that the battery was down here, right, where is it? In this scenario, right? No, you can't see what I'm doing. This scenario. In this scenario. Well, the only reason this works is, you see, this node is not an essential node. That's the one being grounded. So from positive to negative, well, there's no power distribution to something else. All that voltage is just going to go straight to that node. That is why this one is the way it is. Now, for this case here, right? These are two essential nodes. This battery here, right? It's going to distribute evenly the 100 to both these two nodes, but in reality, this whole thing is going to become a 200 volt node here. And one sec. Okay. So how do we do a supernode the way that we normally would, do a KCL? So think of it as, it is one node, but it's like, now we have 4 essential points. Now we have a current here. We'll do current KCL that way, this way, and from Vx this way, and this way, right? So that's what we're going to do. But we're going to use the nodes as a reference point, Vx and Vz. So we're going to do V of x minus VA divided by 4,000 plus VX divided by 5,000. That's the 2 on that side. And then we'll do this one plus. We have a current here. Current controlled voltage source. How do we do that? So I know the one part's just going to be VC minus VA and then this current source is going into it. We'll just do minus 9. Let me check to see. That's a Greek letter. I don't know what it is. It's like a on the thing. It's like that. But I'm gonna put let me check. Let's see if this is correct. Action B sub Z minus B sub A. In this case, it's one problem divided by 2,000 minus 9 I sub Greek letter. What is it called here? Sigma. Alright, yep, mine's correct. This is equal to 0. Okay. I put this whole thing into the regarding this circuit, to a central, connect to a power source, creates a supernode. That I do know. Now, do know that V sub Z minus V sub X is equal to 200. Because if you go from V sub Z to V sub X, right, you do the node, they're equal to 200. Do note this statement is true. Let me plug this in. V sub X minus which that is relating to the first problem of the first question that it asks us. How do they relate? There's a constraint. What it says. So, yeah, that's right. We have 3 more parts to these questions. Alright, so now that we have our KCL, so to note, this equation here is the equation for the constraint for the supernode. So basically this algebraic expression here is equal to the supernode. A little later, figure more out. Oh. There's bro calling. Yo. Schoolwork. Alright, I'm back. Circuit is shown. We'll call that blah blah blah. Express your answer in equation. terms of the labeled node voltage, make sure each term in your equation evaluates to a current in amperes. Alright. Now we need to do a KCL at VY, or VA in my case. This supernode stuff is something I slightly learned, barely. Doesn't make too much. It's not too far-fetched, but it's nothing crazy. So at VY we have, this is part I. The VY is minus, we'll just put VX divided by 4,000. I'm just gonna make it, I might think that would be minus 200 since blah blah blah, but according to the constraint, if you solve it algebraically, Vz is equal to 200 plus Vx. So, I don't know. And I'm just going to ignore that for now. I'm just going to keep going forward until I figure it out. Plus minus V sub x divided by 2,000 plus V sub y. Alright, so this equal to 0. V sub y is V sub a. I just slightly switched back to the problem's variables. Plug these in. The correct answer involves the variable v sub z. Oh shit, which one did I mess up? V sub y minus v sub z. I got that shit wrong. Excuse my French. This, put the wrong variable in tracks. Let's see. Here we go. Now we got that KCL. Now write the constraint equation imposed by the dependent current source. The circuit is shown here. One side of the equation has already been supplied for you. Express your answer as an equation in terms of the labeled node voltages. We're solving for this current. The constraint defines the variable that controls the dependent source. IA, or I sigma. In terms of the node voltages, know that I sigma is the current through the independent voltage source. So we cannot find it using Ohm's law. Instead, recognize that the current I sigma is leaving the node labeled V sub x. So KCL tells us that I sigma must equal the sum of the currents entering the node labeled v sub x. So what's entering? What's entering this node? Okay. So we know that the current entering is v sub y minus v sub x divided by 4,000, and then do negative v sub x, because if you're going from the ground to v sub x, that'd be negative v sub x divided by 5,000, question mark? I think that's right. Let me type that in. Alright, we're going to do v sub y minus v sub x divided by 4,000. Right. Plus negative v sub x divided by 5,000. Oh, who is calling me again? Yeah.
I looked at it.
I'm in the corner. Goofy. It's right. It is right. Okay.
So it can go mobile.
Yeah.
Knock on the door, you know.
From here to here. From here to here. Equal 5 sigma. Which is, in terms of the problem, I used A. Divided by 4,000. Plus from 0 to negative bx. 5,000. Must be equal to I sigma.
Sigma.
Alright, now we're at this point. So how do we solve for this shit simultaneously? So, we have 4 equations. Right? Let's draw a line here. This is where we left off. We have this one. This one. This one. And this one. Okay. These are our equations. Excuse me. So we're gonna solve the nodes. What's the setup you think this would be? Well, if I were to guess, this would be the setup for the first equation. We'll get them all in terms of vz, x, and y. So for the first one, we have vz minus vx. So we have v1 plus vx negative 1 plus vy 0. I'm just assuming this is how it's going to go. Next one. Well, these have I sigma in it. We don't know I sigma. But we can plug this into here. We sure can plug that in. Okay. Huh. This was really weird to set up. Having a variable like I sigma, you can plug back I in. We need to figure out what because we have this I variable here, we need to figure out what that is. So we'll just plug that in. So we have, this would be rewritten as 9 minus 9 plus 9 plus 9. And you got your new formula here. Okay. This is so hard to do. Let me copy all this down here. Okay. So we're going to do xy, that's our format. So b sub c.
Thought you ate that.
B sub z.
Hey, bro.
What?
So I sent my mom that motherboard, the Asus Tough H670,
Mm-hmm.
to buy it, but she found a cheaper one. Nah, it's the Asus. I looked it up, and apparently it's better. She found it's an Asus Tough Z690.
Go for it.
Hmm?
Go for it.
That's what I told her to do. So she's buying it. So I'll finally have a motherboard.
Ship here?
Huh?
Being shipped here?
Should be. If not, it'll be my PC. I talked to Caleb.
Who's that?
Noah's friend, that lemon puff guy.
Yeah, what about him?
He's pretty good with computers. I was talking to him about it. He was like, there's a chance that it actually probably runs. But there's like I forget what he called it, some code. Something. I don't know. Not sure. I'll let you get back to it.
Our piece? 917. Then this VA is VY in this case. Plus negative 1 over 4,000 plus negative 1 over 2,000 that's all of it. Just those two. There should be another one. Oh, there it is. That was for that second one was the KCL at the Supernova. Now we're gonna do this one up top. VZ is negative 1 over 2,000 plus VX negative 1 over 4,000 plus VY 1 over 4,000 plus 1 over 2,000 plus 1 over 8,000. That should be our matrix. Oh wait, do we have any constants by any chance? I think they're just equal to 0. And that second one right here will be equal to 0. That looks ugly, but we'll make sure we don't have any constants. 9. Yeah, I don't see any. I think 200 is the only one. I don't think this matrix is going to work. I doubt it. This is a negative 1, negative 1, 0. And we just use that 0 as a filler since there's no BY for that pressure. 2,000. 1 divided by 4,000 plus 1 divided by 5,000 plus 9 divided by 4,000 plus 9 divided by 5,000. Negative 9 divided by 4,000 plus negative 1 divided by 4,000 It's -1. Using the matrix still. Matrices. Now let's go to our B. We have 200, 0, and 0. Alright. So we have VZ. We have perfect numbers this time. This is working out perfectly. VZ is equal to 300. Vx is equal to 100. And we have Vy equaling 200. Alright. Let's review what we have. So we have, in the beginning, we're using the first equation, which is our supernode. Right, this is the equation for our supernode. This is how you put that down. Then we do the KCL for the supernode. And then we do a KCL at VA. That is this whole thing. And then we do another sort of KCL to figure out I sigma. You know, we do a little substitution here. No. So these numbers, let's see if they're right. They look perfect. So BZ 300. B sub Y is 200. And we have 100. We can plug this into our equation, right? -9 times V sub Y 200 plus 9 times V sub X 100 divided by 4,000. We have 9 times V sub X 100 divided by 5,000. This plus this. Got -45. Like how this works. Never does. My math is always wrong. Let's see what Chegg has to say. I feel like my voltages are right. I just don't know how to do the one part. No, I'm right. Yeah. My voltages are right. My signal's wrong. So what is my math? No. Yeah, I messed that up. I plugged that in, that -9. That -9 is actually not there for this. I'm being stupid. Okay. So yeah, that was my fault. So in the original equation, it's to multiply everything by -9 again. This is a minus. This is a minus. Okay. Now what does that give us? Vy, right, which is 200, minus 100, divided by 4,000. Negative 100 over 5,000. Plus this 0.005, which is 5 milliamps, which is the right answer. Okay, I was off by a little. I just forgot. And those are the bonus questions. So yeah. Let me show. So yeah, 5 milliamps. Our numbers are right for this. And yeah. Okay. Let's go over some of the problems. These are really easy. Basic idea of the node voltage method is to apply the Kirchhoff's current law to every essential node, like we just did, like we've been doing. That is the node voltage method. Can't figure that shit out to save my life. For the circuit in the video, what is the power dissipated by the 25 ohm resistor? So, power dissipated is this current I triangle times the 25 ohm resistor. And I'm sure in the video it gives it to you. 1.5. And 1.5 times 25 is... power is 1.5 squared times resistance. That does not give me that. Dissipated. Power dissipated by the 25 ohm resistor. Oh, I sub triangle is 1.2 actually. 1.2 squared times 25 gives me 36. Okay, I was just looking at the wrong numbers. Yep. Next. This one took a lot of points. In the node voltage message, when a dependent voltage source connects two essential nodes, how can the situation be handled? The dependent source and its two ends are treated as a supernode, like I just did. Right? And a single KCL equation can be written like I did in the problem. When a current-controlled voltage source joins two essential nodes, what unknowns occur in the system of equations produced by the blah blah blah? Well, there's more than just one possibility. I originally thought it was a mix because you have unknowns that are voltages and currents. Well, you can just have one or the other, but you can also have a mix. So all of these possibilities are likely. So this is why this is right. I don't think I did 8. Let's see. For the circuit analyzed in the video, find the power supplied by the 100 volt source. Power supplied. Well, power is equal to current and stuff. There's some math behind that. May or may not get into that. Yeah, I'm at 88. But if I get this one right, I think it brings me to 100. Let's see. See if we can get this right. Find the power supplied by the 100 volt source. Alright. Let's see if we can do that. Real quick. Thought it was gonna work out, but I don't think I have time. I need to bring this over to my other screen. So even without watching the video, let's see if I can solve this. So we have a 100 volt source. We are connected by a couple nodes. Ohms. 10 ohm. 60 and this is minus. Oh, it's cuffed. Let me look at the video, see what it is actually. Okay, this is minus, this is a plus. Ohms. 30 ohms. Alright, let's find our points. This is one whole node. This is a node. This is a node. This is a node. B1, B2, B3. We'll ground this here. Okay. So what can we do here? Well, we know V1 is 100 volts because it's going from ground and this source is connected directly to the V1. So V1 is 100 volts. That's a known. Let's do a KCL. Matter of fact, we don't really have to do a KCL at V1 since it's known. It's a known source. We already know it, so we're good there. This current controlled, no, voltage controlled, I think, for V sub triangle. Need to figure that out. And the voltage drop across here is equal to voltage sub triangle. And the voltage drop from here is V sub 0. So let's do a KCL of V2. So we have V2 minus 100, which is V1, divided by 10 ohms, plus, what do we call that? What would we call this, a current? Oh, it's a voltage controlled source. I believe we would call it a supernode. I believe this is a supernode. So yeah. This here is a supernode since it's two essential points connected by a voltage source. So, what we're gonna do is, since this here little thing here is a node, we'll draw a KCL out of every point from there. So we'll do V2 over 60. Then we'll call this point over there V3. One sec. I think the note is this voltage drop here from positive to negative. We'll notice that that is given the value V delta. So we might as well call this V delta here. Alright. So plus V delta divided by 20 plus B delta over 30. Okay, it's our first KCL. Now we also need to do the one for the for the node, the supernode. So we have V2 minus V delta is equal to 4 V delta. Now let's simplify further. Okay. So we can subtract that over. We can have V2 minus V delta minus 4 V delta gives us 0. Right. So now let's keep them separated. So width is equal to V2 is 1 over 10 plus 1 over 60 plus V delta. 1 over 20 plus 1 over 30 equal to 10. Because this constant here become negative 10, you add it over, you get 10 on the other side. And that's all of them up for that one. And then we'll have V2 1 plus V delta. We have negative 1 plus negative 4 equals 0. Okay. Now let's do a matrix. It'll be a 2 by 2. Divided by 10 plus 1 divided by 60, 1 divided by 20 plus 1 divided by 30, 1, negative 1 plus negative 4. And I'm putting them in a matrix. And we get 75 and 15. V2 is equal to 75. And V delta is equal to 15. Volts. Okay. Alright, now that we've done all that, and go back to the question. Find the power supplied by the 100-volt source. So, power supplied by this 100-volt source here would be equal to the current coming in times that. Possibly. think how I would do this. Power supplied by the 100-volt source. So we need to find the current over there. Oh. We know that the voltage drop from V2 to V1, V2 being 75 minus 100 divided by 10 gives us a current of negative 2.5 this way. Now if we go from V1 to ground, that's 100 divided by 80. That's 1.25 going down. So we have negative 2.5 plus 1.25. And if it's positive, the current going this way would be positive plus I. We would add, it would be 1.25. 1.25 going to that way, to the left. So 1.25 times 100 gives us 125. Wrong. Wonder what's wrong with my math. Let's see. This is quite a conundrum. $125 is not the answer. Okay. Power supply. The current going out is 2.5. So it would be double this. That's wrong too. 250. Two 2.5 to the right, theory. $100. All right, I got the answer. Okay, just by some sheer thinking. So the voltage source is here, right? What is that number? So let's draw what we have so far. We have a node. And we know the current coming down is equal to what? That's 100 divided by 80. 1.25. We know the current going this way is negative 2.5. And you want to know the current that's going this way. So if we draw this, the current coming in would be positive since it's coming towards it, plus 1.25 is equal to 3.75 amps. You also have to note that this is the source. I was doing it wrong. The source must have a greater current as it goes. It must have a greater current than all the other currents going down the line because it has the greatest power, because that's where the power is sourced at. So I'm at 104% now. Whoppy woo. Let's see if we can get number 4 now with my now new knowledge. Okay. Find the power supplied by the current source. Current source. I'm pretty sure in the video that towards the end it gives you the answers. Now for 4. We're just going to focus entirely on the power. What does it want? The current source. The current source. This way, 3 amps. Well, the voltage at this point is equal to what? V2. It's 20 volts. There's another point here. This one is 100 volts. So I had originally thought that the voltage from, what have I tried? Previous answers. -60 is not right, and negative 16.5 is not right. Okay. So power supplied by the current source. What is the current at the voltage source? Let's figure that out. We know this is 100 volts. We know that. We know this is 10 volts. We have this voltage source over here. In previous problems, how did we figure out the voltage generated by the current source? Well, if we're going from V2 to the ground, V2 minus 0, So let's see what happens if I plug in 60 again. I've already tried it before. I feel like negative 60 would be the answer. Because as it's heading towards the node. But it didn't tell me to check my signs or anything like that. The question asks, what is the power supplied by the current source? 3 amps. It has to be negative 60. If it's not, it's definitely not. It has nothing to do with the 20 volt being multiplied by the voltage times current. It has nothing to do with that. What could it be then? What could it be? Well, we know as we go from V2 to V1, right? V2 to V1, V2 being 20, the other one being 100. Divide that by 80. We have negative 1 going that way, so let's invert it. We have 1 amp going that way. Alright. So what's the current to the right of there? Well, go from 20 to 0. 20 divided by 5 is 4. And this way is 4 amps. Which is much greater. So if we go from 100 minus 10, 100 divided by 10, we have 10 amps going down this way. Which must mean this must be 11 amps by theory. Right? Right. We have minus I. Yeah. That's a true statement. This is a tough question. Let me see. This is a tough one, for real. Well, we know the current originating at the source would relate to the last problem. 11 times 144 gives us a number of 1584. And if that's the number, I would shoot myself. Nope. I don't know what the number could be. Power generated at 3 volts. Three amp source. Can't figure that one out. And I'm gonna conclude it there.